So salts like these can act like acids or bases? Yup. Watch this video and in just a few short minutes you're going to completely understand this topic.
What's up, everybody? Welcome to Neil's not so boring world of chemistry. Let's go into the lab and take a deep look.
All right, so let's break this down into some easy steps that you can follow. Step 1, check for solubility. You see, a salt can only act like an acid or a base if it's soluble in water. Now, in order to do this step, you'll need to know some solubility rules. I'm going to be using the rules required by the AP Chemistry exam. So when I look at this list, I start off with sodium fluoride, and because it contains an alkali metal, this is a soluble salt. So it's potentially going to be an acid or a base. Next up, I have iron 2 carbonate. According to my solubility rules I'm using for this example, this does not dissolve in water, and therefore, it's not going to be acidic or basic. Finally, we have aluminum nitrate. The presence of the nitrate ion typically means that the compound will dissolve. So I'm also going to mark this as a potential acid or base. Okay, that's step 1. Let's go on to the next step and think about what happens when these two soluble salts actually dissolve in water. Now we're ready for step 2. What I've done on the board is I've taken my two soluble salts and I've split them up into their respective ions, because this is what happens when soluble solids are added to water. They dissociate. The questions about this topic are really asking you whether the ions that make up these ionic compounds are acids or bases, not the entire compound itself. So how do we figure this out? Well, firstly, we need to know our strong acids and our strong bases. I would advise you to have these committed to memory. Next, we're going to look at each individual ion and ask ourselves, does that ion show up in the formula of any strong acids or bases? Let's start with sodium. Na+ doesn't seem to appear in any of my strong acids, but I do see that sodium occurs in sodium hydroxide, the strong base. Because sodium is part of a strong base, it cannot be acidic or basic when it's on its own as an ion. So I'm going to eliminate it as a possibility. Next, let's go to fluorine. Do you see fluorine in any of the formulas in front of you in these two categories? No. Fluorine is not part of any strong acids or strong bases. So this may have the behavior of an acid or a base. Next, let's go to aluminum. Once again, you will not see aluminum in any of the formulas in front of you, so we need to consider aluminum as a potential acid or base. Finally, we have nitrate. And when you look at your list, you will find the nitrate ion, NO3- as part of nitric acid. Because of that, we are going to eliminate that. Nitrate will not have acidic or basic behavior. So in step 2 of this process, we're able to hone in on specific ions, and in part 3, we're going to ask ourselves, will they act as an acid or a base, and why? Okay, I hope you're ready for part 3, because now we're going to finally solidify our answer. So just as a reminder, we've decided that F- and Al3+ are both potential acids and bases because they were not part of strong acid, strong base formulas. So we have a rule we can remember to decide whether one of these is going to be acidic and the other basic. And the rule goes as follows. Ions of weak acids are always basic. Let's talk about what that means. F- is an ion. F- can be found in the acid HF. HF is not a strong acid, it's weak. How do you know HF is a weak acid? Well, it's not one of the 6 strong acids that you've memorized. So because F- is an ion of a weak acid, HF, it's going to be basic. So to the original question, is NaF acidic or basic? We now know that it's going to be basic because of the presence of F-. Let's go to aluminum. The other rule is ions of weak bases are acidic. So as you can see, aluminum is part of a weak base, aluminum hydroxide. How do you know that aluminum hydroxide is a weak base? Well, it's not one of the strong bases that you've memorized. So because it's an ion of a weak base, it's going to have acidic behavior. Now, the original question asked, is aluminum nitrate acidic or basic or neither? We now know that it's going to be acidic. So we've got two compounds. We've been able to decide whether they were acidic or basic by splitting them apart, looking at the individual ions, comparing them to our list of strong acids and strong bases, and following this simple rule. Next, let's take a look specifically at how this basic behavior happens. Hey, welcome back. So we've got a really nice and neat, easy rule to remember whether an ion is going to be an acid or a base, right? But what about the concept? Do we understand why F- is going to be basic? Let's make sure we do. On the board, I've written the equation for HF, a weak acid, turning into H plus and F minus. Now, I'm sure by now you know strong acids come apart really well, while weak acids like this don't. So the HF is written really big and the ions really small to signify the fact that most of the HF molecules do not split up, and a very small number of them do. But mostly, HF stays together. Why is that important? Because it tells me that the bond between hydrogen and fluorine in this weak acid is really strong. That's right, weak acids actually have very, very strong bonds holding them together. So let's take that knowledge and look at this model. We've already decided that if we have the salt sodium fluoride and we put it in water, the ions are going to separate. We also decided that sodium is not a player because it's part of a strong base, so we're going to take that out of view. Now, what's going to happen with the F- when it's around water molecules? Well, think back to this. We said H and F bond really well. So this F- ion will be attracted to a hydrogen, pull it off of the water molecule, making that very strong bond in the HF, and look what remains. F- is able to generate hydroxide ions. Now, we also know that when hydroxide ion concentration is bigger than H+ concentration, we get a basic solution. So F- acts like a base for this reason. It's able to pull hydrogens off of water, make that really strong HF bond, and the resulting hydroxide ion concentration is going to be high, and this is going to give us a pH well above 7. Okay, let's come up with a strategy so you can solve these sorts of problems on your own. Step 1. Use solubility rules to decide whether or not the salt will come apart in water. If it doesn't dissolve in water, it can't be an acid or a base. Step 2. Take that soluble salt and separate its ions. Eliminate any ion which is part of a strong acid formula or a strong base formula. Step 3. Use this simple rule to decide if the remaining ion is acidic or basic. If it's the ion of a weak acid, it's going to be a base. If it's the ion of a weak base, it's going to be acidic. Okay, now we're going to do a practice question. Classify each of the following salts as either acidic, basic, or neutral. Sodium acetate, potassium chloride, ammonium chloride. Pause the video, come up with your answers, and unpause to check your work. The first is basic. The acetate ion in particular is the ion of a weak acid. Potassium chloride is neutral. Both ions are part of either a strong acid or strong base formula. Ammonium chloride is acidic. The ammonium ion, NH4+, is the conjugate of a weak base, ammonia. Now let's watch this video. As each salt is added to distilled water, check for a color change against the guide provided. As you can see, the potassium chloride is green, while the sodium acetate is blue, and the ammonium chloride is yellow. Thank you so much for supporting the channel with your comments, questions, likes, and subscriptions. I truly appreciate it. If there's anything about this topic that you need further clarification on, please let me know below, and I'll be sure to get back to you as soon as possible.